All right, Mr. Boothman back for the last section of this unit, and I'm getting tired. I'm recording all of these in one shot, so let's go ahead and get this done. Um, but this is an important section, and it's so interesting because we're actually taking everything that we've just learned and we're applying it to the real world. Because hey, math doesn't just exist in math class, contrary to popular belief. And these questions will show us exactly where we use this stuff in finance, in science, out in the real world. So let's take a look. First, we're going to look at applications of exponential functions. First, we're going to look at interest, specifically compound interest. So a lot of interest is compounded. And this first example is fairly common. So you have a sum of $1,000 and it's invested at a rate of 12% per year. We want to find the amounts in this account that we've invested our sum in after 3 years if the interest is compounded annually, semi-annually, quarterly, monthly, and daily. So I hope we all understand what interest compounding means. Interest, of course, is a bit of money that you earn when you invest a sum of money. And then it compounds, it adds to itself every so often. So either once a year, twice a year, 4 times a year, once a month, or once every day. So all of this compounding interest is governed by one equation. That is A t equals P times 1 plus R over N to the NT power. And that's it. I'm joking, of course. I'm going to explain this because there's a lot of variables here, but it's all very straightforward and we're given almost all of the information, I promise. So here, A of t, that's the ending amount, A for amount, whatever we end up with as a function of time. This P is the principal, that's the starting amount. 1 is 1. Hopefully you know that. R here is the interest rate as a decimal. N, so N is here and N is here, is the number of compoundings, the number of times it compounds per year. And then T is the total number of years. I'm using the hashtag sign as number because I'm too lazy to write out number, and it would make my handwriting too messy anyway. So that's what each variable means. And again, like I said, it looks like a lot, but we actually were given almost everything in the problem. So P is 1,000. That's what we're starting with. R is 0.12. 12%, we have to convert that to a decimal. 12% is 0.12 as a decimal. Now we want to find the amount that we have after 3 years for each of these different schedules, compounding schedules. So annually, A equals 1,000 times 1 plus R is 0.12 over N. Annually means we're compounding once a year, so N is 1, and then our T is 3 in 3 years. If I plug all of this into a calculator, I will get about $1,404.93. So that's really not bad. After 3 years, I made over $400. So I almost made 50% of what I put in. That's pretty great. Semi-annually, let's see if our number goes up even more. Semi-annually, most of this is the same. I'm starting with 1,000, 1 plus 0.12 over. This time, semi-annually, I'm compounding twice a year. So N equals 2. I still have 3 years for T. And if I plug this into a calculator, I will get $1,418.52. So, hey, I made about $14 more than if it compounded just once a year, going from once to twice a year. It's even better. Let's see if it continues to go up. So let's try quarterly. A equals 1,000 times 1 plus 0.12 over quarterly means 4 times a year, 4 quarters. 4 times 3. Plug this into a calculator. I get $1,425.76. Went up $7, so I went up $14 going annually to semi-annually. I only went up about $7 going semi-annually to quarterly. Looks like my growth is slowing down a bit. But still, let's take a look. Let's try monthly. A equals 1,000 times 1 plus 0.12 over. Monthly means n equals 12. 12 times 3. I do apologize, my writing's getting really scrunched there on the side. So that's 1,000 times 1 plus 0.12 over 12, all to the 12 times 3 power. If I plug that into a calculator, I get $1,430.77. It is slowing down. Now I only went up $5. Let's see how much I go up if I go from monthly, 12 times a year, to daily, 365 times a year. I feel like that should go up way, way, way high, but we'll see. 365 times 3. Plug that into a calculator, and I get $1,433.24. Wow. So going from 12 times a year to 365 times a year, I only went up another $3. What's going on here? Looks like the rate of increase is slowing down. Actually, it does slow down, and it will approach a number. And someone a long time ago, actually a few people, but of course, old white men, as I like to joke around in class, saw this and discovered that if I go up to compounding continuously, I'm approaching a certain number. So as I went from monthly to daily, my growth was slowing. If I go from daily to compounding constantly, all the time, continuously, I will approach a definite number. And the number that I approach there is related to E. In fact, that's where E comes from, this compounding interest formula. So if I'm compounding continuously, my compounding interest formula changes a bit. This is A of t equals P times E to the RT. And that's it. Much simpler. So A of t again is my ending amount as a function of time. P is my principal. It's my starting amount. E is the constant E. R is my interest rate again as a decimal. And then T is my total number of years. All right, so they want us to find the amount after 3 years if the interest rate for the problem above was compounded continuously. So let's go ahead and try this. A equals 1,000 times e to the 0.12 times 3 power, which is about $1,433.33. So if I compound my interest as often as I possibly can, continuously, that's the maximum amount that I will get at 12% interest over 3 years. Still a decent amount. I made $433.33 in just 3 years. but not quite as high as you might expect if you're compounding continuously. Very interesting, and we can explore this a little more later on, and you will definitely think about this more deeply once you reach calculus. And if you go on to business or finance in any way, then you will absolutely see these equations again. For now, though, we are going to look at a couple of other exponential function models. So we're going to return, I promised we would, we're going to return to exponential growth and exponential decay. So if you'll remember, exponential growth, sketching a quick graph looked something like that. Exponential decay looked similar, but it was kind of mirrored. Looked something like that. Model now, like we want to be able to write this as a model, as an equation. So we can take real-world situations and apply exponential growth or decay to them. And to do that, it's going to look very similar to the formula we just wrote up here. A of t equals p times e to the rt, where a of t is the ending amount as a function of time, p is the starting amount, principal, except we're not always talking about money. We have the constant e. R for exponential growth is the growth rate. This is positive. And then t is the time. For exponential decay, then, it's actually the same formula. Except this time r is the decay rate, and this is negative. And we'll know that it's negative because in the problem, it will say that we're decreasing. We're depreciating. Bacteria are decaying. They're dying. And everything else here is the same. T is time, P is the starting amount, A of t is the ending amount. And then R is still our rate, but it's negative in this case. So let's take a look at some examples and actually apply these formulas. We can model real-world situations using these formulas. So if the world population in 2000 was approximately 6.08 billion, and right away, if I'm going to have to use that number, I'm going to write this in scientific notation. 6.08 times 10 to the 9. 10 to the 9 is a billion. The annual rate of increase was about 1.26%. And right away, I see this percentage. I'm going to write that as a decimal, so I can actually use it in my rate. R equals, this is a rate of increase, so it's going to be positive, and that's 0.126. So write a function to model world population growth since 2000. Well, I know I'm using my model up here. A of t equals my starting amount. So if I'm starting in 2000, that's 6.08 times 10 to the 9th times e to the, my growth rate is 0.0126 t. And then t is what I'm plugging in. And that's it. That's really all that I have to do here. Use the model from part A to predict the population in the year 2040. So from 2000 to 2040 means that t equals 40. Excellent. I hope you all got that right. So I'm looking for A of 40 equals 6.08 times 10 to the 9th times e to the 0.0126 times 40. If I plug that into a calculator, I will get about 10 billion people by 2040. If you're curious, we have already passed 7 billion. I think we're well on our way to 8 billion. So 10 billion really doesn't seem too far off from here. Let's take a look at example 4 then. Computer valued at $6,500 depreciates at the rate of 14.3% per year. Depreciates, so right away I know that R is negative. And then at a rate of 14.3%, so R will be negative 0.143. I'm converting my decimal, or I'm converting my percentage to a decimal. Write a function that models the value of the computer. Same formula, a of t, and before you ask me, and I know some of you will still ask me in class, yes, you need to memorize this formula. It's basically one formula for exponential growth, decay, compounding interest. Please, this is very important. So a of t equals my starting value, 6,500, times e to the r, which is negative 0.143 t. That's all there is for a. B, I want to find the value of the computer after 3 years. That means t equals 3. A of 3 equals 6,500 times e to the negative 0.143 times 3. Plug all that into a calculator. I will get about $4,232.54. So after just 3 years, my computer is worth more than $2,000 less than it was when I first bought it. Now, unfortunately, this is true of a lot of things that you buy. All your electronics, when you buy a car, value depreciates. All right. One more application. This time we're looking at applications of logarithms because there are a number of them. We've talked about a few in class, at least I've mentioned them before. Today we're going to go through an example using sound. So I'm sure we've all heard the word decibel. Sound is usually measured, or at least volume is usually measured in decibels. Given by the formula, volume in decibels equals 10 times the log of I over I naught, where I naught, I sub 0, is the threshold sound that is just barely audible. So I naught, that's just a fancy term that we use to refer to a sound that barely exists, the smallest sound that we can hear. And then I is the intensity of a sound measured in terms of this I naught. So I could have a sound that's 1,000 times I naught, or 10,000, or 300, or 10. And then if I plug that into this formula, take the log, multiply by 10, I will get the volume of my sound in decibels. So decibels are thus measured on a logarithmic scale. I'm using the log here. That means that I go from one step to the next. I'm not just increasing by 1. I'm at logarithmic scale, and this is true of like the Richter scale for earthquakes and a lot of other scales, that as you go up one step, you're going up a factor of 10. So the Richter scales, you go from 1.0 magnitude to 2.0 magnitude. That's not just increasing by 1. It's increasing by 10. Go from 1 to 3, that's 100. 1 to 4 is 1,000. So logarithmic scales get really big really quickly, just like exponential scales do. So let's look at an actual example. Example 5, prolonged exposure to sounds above 85 decibels is dangerous and can result in hearing loss or damage. Your friend decides to scream in your ear at, let's count the zeros here, 1, 2, 3, 1, 2, 3, 1, 2, 3, 97,900,000,000 I naughts. If she keeps screaming, could this cause hearing damage? Now you might say, well, obviously, that's a huge number, but of course we're taking the log, so this could end up being a much smaller number. We need to take a look. So our volume, plugging into the formula, is equal to 10 times the log of 97,900,000,000 I naught over I naught. Again, I'm plugging into this formula. My I naughts cancel, so I have 10 times the log of 97,900,000,000. And if I calculate that log in a calculator and then plug in or multiply that by 10, I will get about 109.91 decibels of volume. This is higher than 85 decibels, which is considered the danger threshold. So yes, there will be hearing damage. If it goes on long enough, you could lose your hearing. So I think it's time to find a new friend if that happens. But for now, hopefully your friend isn't doing that to you. Although I can think of a few of you who would actually do that to each other. If you don't have questions, that's awesome. If you do have questions, you're confused by any part of this video, go ahead and rewatch it. Bring them to class. I'm excited to finally be able to talk about things in the real world, because I know that a lot of this class so far has focused on the math and the theory, and I promised that it wouldn't be the major focus. So I'm glad that we're finally getting into this stuff. So I hope you enjoyed this. I hope you've had a good unit so far. I hope your quarter's going well, and I will see you in class. Have a great day, and thank you so much for watching.